Grateful to be here, so thanks a lot for the invitation to be here in nice Korea and nice Kias.
Can you speak loud?
Yes, I can speak very loud. Okay, I think it's quite efficient, so. Okay. Okay, so the title of my talk is the Feng-Rao bounds. So those of you who know this topic maybe is a little wonder why it's bounds and not bound, why it's in plural. So I hope it will be clear during the talk why I'm calling it, it's bounds in this title. So in this conference there are talks about codes over rings, but in the literature mostly codes over finite fields are considered. So code over a finite field, well, it's nothing but a linear subspace of f cubed to the power n. So how difficult can it be? I mean, how can we do research on that? So the only thing we have is we have vector addition and scalar multiplication. This is the only operations allowed. But still we are interested in these three parameters n, k, and d, and of course the length n, the dimension k, can be dealt with using a standard linear algebra approach. But when it comes to the parameter d, well, then we need something more. And what I claim is that the operation that is really important, basically important when we are trying to deal with d, and actually also sometimes with k and n, is this component-wise product. So, and this will be extremely important during my talk, so please make sure to understand what I mean by component-wise product. Yes. It is what it says, component-wise product. Yes. Okay, so my claim is that when we use algebraic geometric codes or Reedmuller codes, weighted Reedmuller codes and so on, affine variety codes, then the game we play actually is about trying to find out what is going on at the code level with respect to the component-wise product. Okay, so I have three levels of abstraction here. So I would say the green level is the most high theoretical level. So I call it higher algebra. That would be algebraic geometry or function field theory or something like that. At an intermediate level we have multiplication in quotient ring. So that would be affine variety codes or Reedmuller codes and these kind of things, where we have a polynomial ring and maybe an ideal that we do calculations modulo. And then at the very lower level we have the codes themselves. So I'm saying that the multiplication at the higher level or intermediate level translate into component-wise product at the lower level. So information derived up here or up here gives us information of what is going on about the component-wise product at the very lowest level. But then there are also some errors here. So what I'm claiming is that if we have a higher level description, then often it can be translated into a quotient ring description. And the error the other way around is about, well, if we do that, then maybe we can take some information that is easy to derive over there and take it back to the higher level. So that is one point of view in this talk. Another point of view is to talk about dual code versus primary codes. So dual codes, well, this is of course codes defined by parity check matrices. And the usual Feng-Rao bound, which is just what we call the Feng-Rao bound, is about dual codes. But I would like that to be maybe in the proof to be called the Feng-Rao bound for dual codes. I'll argue why. When you have some kind of supporting algebra, like a one-point union of L spaces from a function field of transcendence degree 1 or an generalization to a higher transcendence degree algebraic structures, then this bound is called the order bound. So over here when we study primary codes, of course codes defined by means of a generator matrix, well then we have, if we have an intermediate level where we have a polynomial ring modulo an algebra, then we have the footprint bound, which is a method to estimate how many zeros, how large a variety can be. So this gives us a way to estimate the minimum distance of a code. And then Andersen and I, we derived a bound which has very much the same flavor as the Feng-Rao bound, except this is for generator matrices rather than for parasitic matrices. And it's obvious there should be a connection. So today I will talk about that connection, and I mean it's so much connected so that I would suggest we in the future call this bound the Feng-Rao bound for primary codes. So as part of the talk, I will talk about the connection between these two bounds. Okay, so in my talk I will talk about connection between levels of description. I'll talk about connection between dual and primary description. And the results, well, it comes out of consequences of the connection between the different levels and primary and dual description. And my results were will be derived from the medium and low level point of description. So what I will not cover are very important results like what we have here, the Balin bound, Dors-Makiro-Park bound, Libras-Amoros or Solomon method. We have both Lee and Park here, so yeah. So I will not, I mean, these are higher level descriptions, so I will stick to the more lower level descriptions, and we will hear more about your bound on later this week, I hope, yeah. Yes. Okay, so I'll start by talking about the intermediate level, which is a polynomial ring modulo an ideal level, quotient ring level. So we have a general ideal here, J, and this is a polynomial ring in m variables. And the footprint, well, it's very important in this talk. The footprint is the set of monomials that cannot be found as leading monomial of any polynomial in J. So you can say it's a complementary of the leading monomials. It's all the monomials that are not leading monomials. And then, of course, I'm interested in ideals that lives in FQ of x1 up to xn. So I use this standard notation. If I have such an ideal, I will extend it with the defining equations here, explaining us that we are in a finite field. So I have an ideal, I extend it with these m equations. This ideal I will call IQ. And the footprint bound, well, it actually says that an ideal can have at most as many zeros, or the variety of an ideal can be at most as large as the size of the footprint. And if it's a radical ideal, and if your field is algebraically closed, then we have equality. And I mean, these equations here, or polynomials here, makes it radical. And I mean, we can also go to the algebraic closure because we have these equations explaining us that we are actually working in FQ. So we get equality. So for this type of ideal, we know that the number of zeros is exactly the size of this footprint. So what we need to do is to find this footprint if we want to know how many zeros we have. Okay, so two examples. The first example is the most simple thing we can do. So the only equations we have are the field equations. And the footprint, well, we have x to the power q as leading, y to the power q as leading, so the footprint definitely is contained in this set. Actually, this is the footprint. Because we know that we have q to the power 2 zeros. And I mean, this set is always of size q to the power 2, so we have equality. A little more involved, but still rather simple. We take the Hermitian polynomial here. And of course, again, the field equation. Now it's q to the power 2 because we are working over fq to the power 2. And if I choose a monomial ordering such that y to the power q becomes more important than that one over here, then this becomes leading. Well, then here we have a restriction. No powers of y larger than q minus 1. And here we have a restriction, no powers of x larger than q squared minus 1. So the footprint will definitely be contained in this set here. And then again we play the game to actually see how many zeros we have. So this is a norm and this is a trace, and playing with that we see that we have q to the power 3 zeros, and this set is of size q to the power 3, so actually this is the footprint. So think of it, what we're talking about right now would be a way of estimating the length of a code, because we're interested in points we want to evaluate in. Okay, so just to explain what is a group basis actually, well, it's a basis from which you can easily read off the footprint. So more formally, a group basis is a finite set of polynomials from your ideal. And then we have some monomial ordering, of course, and such that any leading monomial in the ideal is divisible by some of the leading monomial in the defining sets. So this is a group basis. And the nice thing is that from a group basis you can extract information about the footprint directly, and therefore also about the number of zeros. Okay, so this should have something to do with coding theory, right? So what we do is we take an ideal I, then we extend it with the field equation, then we have IQ, we get some points, P1 up to Pn. So this is the points we'll use for the code construction. So a code word will be made by taking a polynomial and then evaluating in these n points. And then the question, what is the Hamming weight of this code word? Well, it actually, the number of entries, there are n, minus the number of zeros in the code word. But zeros in the code word, well, we evaluate in zeros of the ideal, and then should also be a zero in the polynomial. So it's actually this number of zeros we can have in the code word. The size of the variety of the ideal IQ plus what is generated by f. Okay. So assume we have some information, of course we have some information on how we construct our code, so we have some information of what could possibly be the leading monomials. We have information of how we choose these polynomials. What could possibly be the leading monomials? Well, then from that we can, like say, take the worst case, look at all the different possibilities, and get some information of what could be the minimum distance. And of course we can also see if some monomial is not so nice to have as a leading monomial because it would give a bad value of a low value of the Hamming weight. Well, we can just leave it out. So we have a way of improving constructions. So that was the minimum distance. What about the dimension? Well, that's even more easy. So actually this result is what is behind the footprint bound. Namely that if we consider this quotient ring, then it has dimension as a vector space over F. And actually the basis is basically the footprint. That's basically the basis for this quotient ring. So that means if we want to construct a generator matrix, what we do is just we take k different monomials in the footprint, for instance, and evaluate in all our points, and then we get a code of exactly dimension k. Yes. So let's see how it works. In the most simple case, the Reedmuller codes, I'm considering F5. So this is my ideal. I take a code word here, and I don't know what is F, but I have some information about the leading monomial. The leading monomial is x to the power I, y to the power j. And then I'm claiming the Hamming word of this word will be this much, at least. And how do I arrive at that? Let's see. So it's n minus the size of the footprint of I5 plus f. Okay. So assume f has leading monomial x to the power 3, y to the power 2. So we are here. So what I basically want to do is calculate the size of everything, that is n, the size of everything, means what is now excluded because I now have f here. So of course this is excluded because that's the leading monomial of f, but then so is all multiple of it. So all these are excluded, and if you look at it, it's actually 5 minus 3 is 2. 5 minus 2 is 3, and 5 minus 3 is 2. 6 numbers are excluded here. And actually, this will be the minimum distance. Actually, you can find a polynomial with having this as leading, having this number of zeros, actually. So this is how this number 6 came up here. And it's the same game I've been playing with all the other numbers. The same game, simply. So If we are here, we take Reedmuller codes where we go up to degree 4. Then we have all these monomials in the generator matrix. And if we look over here, we have all these estimates of what can be the Hamming weight. So the worst thing is 5. So what we can say is the minimum distance is at least 5. Actually, it is 5. And here, we can have an improved construction, because if already we accept that the minimum distance is only 5, well, we can include these two numbers for free. So we increased the dimension by 2. We didn't pay any price for that. Okay, so that was the most simple case. So the second most simple case was the Hermitian. So again, this is just the usual suspect from before. Now we want to have a weighted degree ordering on our polynomial ring. I said before we want this to be leading, so and we actually want something more. So what we do is say the weight of x is q and the weight of y is q plus 1, and then we extend this to a monomial ordering like this. And then we have this weighted degree lexicographic ordering, that this monomial is smaller than that if the weight of this is smaller than that. And then of course it can happen that the weight is the same, but then we break ties with a second monomial ordering, and in this case it's a lexicographic ordering with y being larger than x. Okay, let's see how this works. So now we're working over F4. And here's the footprint of this ideal up here. So the code will be of length 8. And what is written here is actually all the weights. So the weight of x was 2, the weight of y is 3, and then as a consequence we have the rest of the picture here. That's all the weights we have there. And then I'm looking at a code word here, which is generated by some polynomial, evaluated in our 8 points. So let's try to play the game from before, but do something more. So assume the leading monomial of f is y. So this is the leading monomial. So we can say, if we play the game from before, we can say that the Hamming weight will be at least 4, because we hit this one, this one, this one, and this one. But look, as I claim, we also hit this one. So we go from immediate, so we have the information that the Hamming weight will be at least 4, but actually we can also say it will be at least 5. So look how it comes up. So we take our polynomial, which has leading monomial y, and then we multiply by I. Why? Doing that, we are still working in this ideal here. And if we take the remainder model, this polynomial, well, this is already in here. So taking the remainder, we are still in here. So what we are trying to do now is we're trying to find monomials that are leading monomials in that ideal, but are not leading monomials in that ideal. That is what we are trying to do. So I take this product, remainder, and the leading in the first place is y squared, but y squared is reduced model this equation to something with x to the power 3. So the leading monomial will at the end be x to the power 3. So that's down here, and this is how we actually get from weight 4 up to weight 5. So the claim is that we can actually only have to look at the weights. We don't have to play all this game, we just have to look at the weights. So what I do is I'm saying the weight of y is 3, so I'm just going to all these numbers and I'm saying I can hit 5, I can hit 7, I can hit 9, but I can also hit 6, because 3 plus 3 is 6. So what I only have to do is count the numbers I can hit. So that's not so difficult. So we don't have to play all this story. So if I go to a higher or larger field, so it's again the Hermitian, and now it's over F9, and the weight of x is 3 and the weight of y is 4. So these two will have the same weight, and this is actually what makes the whole thing work. So this will be the footprint again of this ideal. And let's say the leading monomial is x times y to the power 2. What will be the Hamming weight of the corresponding code word? Well, again, we can say we hit all these guys, but we hit something more. We actually hit 15. Why do we hit 15? Because 11 plus 4 is 15. It corresponds to, we have x times y to the power 2 multiplied by y, and then reduce modulo this thing, but we don't have to think about that, we just have to play with the weights. So this is how this 16 came around, this 8 plus these 8 here. And we can play the game with all these numbers, and we get this information. Okay, so now we should talk about the higher level. So 1-point geometric Gobble codes, or 1-point algebraic geometric codes, we call them nowadays. So we have n plus 1 rational places, or FQ, and to construct this code, well, what we need is a basis for this union of L spaces. And the nice result is that actually this union of L spaces can be translated into a polynomial ring, a quotient ring, like this. And actually all the rational points that we will use to evaluate in can be considered as affine points. So everything is very easy if we can find this description. So the result is this description exists. So in this description, of course, the way of estimating the minimum distance, well, that is through the footprint bound and nothing else. So let's do what we did with the Hermitian codes. Let's try to do that at a more general level. So we have Q is a rational point, and we consider the union of L spaces corresponding to that rational point or rational place. And then we consider all the Weierstrass, related Weierstrass semigroup, and it's of course finally generated. So say the generators are W1 up to WM. And this is to prepare for the quotient ring description. So what we do now is like we define a weighted degree or a weight of a monomial simply by saying the weight of x1 is W1, the weight of x2 is W2, up to the weight of xm is Wm. And then of course it translates into monomial function like this. And this makes it possible for us to have to define a weighted degree ordering on a set of monomials. So we said this monomial is smaller than that monomial. Well, if the weight of that one is smaller than that one. Or they may be the same, but then we should have a way of breaking ties. So that is just some monomial ordering we use. There can be the lexicographic ordering. And I already mentioned, the example I gave is of this kind. So here we have two generators, Q and Q plus 1 in that case. Okay. So if we have an ideal generated by F1 up to Fs, if it satisfies these three conditions, we'll say that it satisfies the order domain conditions. And we should have some weights also, weight W1 up to Wm, and we have m variables in our polynomial ring. Yeah. So the conditions are, these polynomials that generate the ideal should constitute a Accrual basis with respect to weighted degree ordering of some kind. That's the one thing. The polynomial in our basis should contain exactly two monomials of the highest weight. And finally, if we look at the footprint corresponding to this ideal, then it should contain no two monomials of the same weight. And this was exactly the situation that we had before with the Hermitian thing. That was what it made us able to do this calculation with playing with the weights rather than doing actual calculations with monomials. Okay, so for a Hermitian polynomial, these things work. We have one polynomial, so one polynomial is definitely a Accrual basis. There were two monomials of the highest weight, namely x to the power q plus 1 and y to the power q, and no two monomials in the footprint were of the same weight. Okay, so what makes this higher level description and the intermediate level description the connection is this result by Miura 97, Pelikan 2001, independent of each other. So let's say that this union of L spaces is actually a quotient ring. And in this quotient ring, this ideal and the corresponding weights, which are what we get from the valuation, minus evaluation, is satisfies the order domain conditions. And as a corollary, if you think about it, actually the rational places you evaluate in, you can consider them as affine points. So this really becomes something very concrete if you have this description. And even better, you can apply the footprint bound, and what you get is something that is always at least as good as the goblet bound, and sometimes better. Okay. So I mentioned that sometimes you can go for the intermediate level to the higher level. So this will be just a quick example of that. So assume we have a function field with a rational place that has a certain Weierstrass semigroup. So here it's generated by lambda 1 up to lambda m. And then the claim is that the number of rational places in this function field is at most equal to this number. And you could derive this bound in the higher level language, but we realized it from our understanding in the intermediate at the intermediate level. And I think you will be able to see the connection, because where does this part come from? So it's again something we have the weight of a footprint somehow, but then we subtract what we hit inside the footprint, because we are counting number of zeros. Yeah. So what does q times lambda I come from? Well, it comes from this field equation. xi to the power q minus xi. So what would be the weight here? That would be, if the weight of xi is lambda I, the weight of this guy would be q times lambda I. Okay. So this is actually the footprint bound we use here. And then plus 1, because we also have the point that corresponds to the L spaces. Yeah. And this result, if you look at a very small q, it's actually better than Serre bound. If you go through all possible Weierstrass semigroup you could actually have. And for higher q, it gives you some information on which Weierstrass semigroup, given genus, how many numbers of zeros can you actually have. Yes. Yeah. So order domains, it's a kind of algebraic structures, and they are, you can view them as generalization of this union of L spaces. And so the thing is that they can be of higher transcendence degree, don't have to be of transcendence degree 1. So and the result is that the transcendence degree of the order domain, well, it corresponds to where the weights lives. So if you have a curve, the weight will be integers. But if you go to higher transcendence degree, well, you have to accept that the weights lives in naught to the power I instead. And that's just the way of doing it. So having this, we have an immediate way of generalizing algebraic geometric codes to higher transcendence degree. So what you could think of is that Reedmuller codes is the higher transcendence degree version of Reed-Solomon codes. So then you have a picture of what is going on. And everything works. The order domain conditions, this correspondence works still. And the footprint bound, all the method for estimating still works. You can do this at a very abstract level, which some people do. Or you can do it very concretely with quotient rings and polynomials and this kind of thing. So let's recap before going on. What we have at the intermediate level, we have an ideal. Consider the footprint here. And we have a code word here, where we evaluate some polynomial f in our points. And if the leading monomial is mi, then we can say that the Hamming weight of this word actually is the number of elements that are in this larger footprint, but not in this smaller footprint. And this can be, well, written in words. It's a number of elements in this larger footprint, which are not leading monomial of any polynomial in this ideal. And this can be translated into, well, let's go down here. Something with the weights, right? If we have the order domain conditions. Then can be translated into the weights. So we look at all the weights in the footprint of the defining ideal. But then we only count those that are also weights, so to speak. Well, so this is only a bound, yeah. So we take the weight of our leading monomial and then add all the weights that are in the footprint, and we count the intersection of these two sets of weights. So this is an easy way of estimating the Hamming weight. So now I'm going to do something ugly maybe for some of you. So I'm going to the very lower level. So if you have not seen this before, it looks very complicated. But the thing is, this is the most simple thing compared to the higher or intermediate level descriptions. But of course, if it's not used to it, it looks ugly. But not so much actually goes on here. But if it's first time, I'm sorry, it will be confusing. So we're talking about linear codes. So we have a basis for fq to the power n. So this is the most important basis we will have. b1 up to bn, that will be the basis from which we'll make the code. And then we have a second basis over here. It's only to support the estimation of the minimum distance. And I really need it in a moment. So I'll put it here now. Okay. Then we have like a filtration of fq to the power n. We have, well, only the 0 word. We call that L0. Then we take the span of b1, that is L1. Span of b1 and b2, that's L2, and so on and so forth, up to the span of everything, that is Ln. So we have like this nested set of codes defined from our basis B. Okay. And what we would like to do is, before we played this game with monomials, leading monomial time another monomial, and where did it end up, and this kind of thing, we want to play the same game here at a very low level. So this is, we have an ordered pair ij, and this ordered pair, well, what we're interested in is the component-wise product. So we take bi and uj and make the component-wise inner product. Of course, this ends up in fq to the power n somewhere. And where does it end up? Well, we have this function rho. This function rho, it tells us where did we end up in this filtration. So this is, maybe I should draw a small picture here. So we have only the 0 word here, and then we have b1 here, the span here, so that is L1, L2, and so on, Ln. So this is the picture. So this row function explains us where we are. Yeah. So we are in here, the row function will be 1, we are here, but not there, the row function will be 2, and so on and so forth. Yeah. Okay, and we will say that such an order pair is one way well behaving. If we replace the first bi by another bi prime, where I prime is smaller, then we get something that has lower row value. So I hope you somehow feel there is a connection to this polynomial thing I played with the leading monomials. And the thing is that if we have some information of our supporting algebra, then we can extract information regarding this kind of thing. And I'm claiming that is actually what is going on. So what you can think of is, think of B equal to U is actually corresponds to these monomials. So what I'm talking about is the Reed-Solomon code now. So this would be bi plus 1, this would be bj plus 1. And so I plus 1, comma j plus 1 is one way well behaving, sometimes and sometimes not. Well, if we end up inside the basis, then this will be one way well behaving. If we get outside, if this number I plus j is too large, we sort of get back because you have to reduce model x to the power q minus 1, x, and then everything is destroyed. Yeah. So here is a notion for what we hit. So it's again the game from before with the monomials. Now it's just on the basis of the code words. So we have an index I, which is a number between 1 and n. And I'm interested in how much can I hit in a one-way well-behaving way. So that means I have ordered pairs I comma j such that the row of bi asterisk uj is L. And then this couple has to be one way well-behaving. Okay? And the theorem is, if you have a code word which has order value I, it lives in Li but not in Li minus 1, then the Hamming word of the corresponding word is thus least equal to this sigma value. Okay? And I claim that the proof is this symbol. So the thing is, we have this correspondence between higher level description and lower level description, and if we want to say something about the minimum distance, we only have to give this proof, which is 4 lines long. So the only thing we need is a way to translating information about multiplication to component-wise multiplication and one-way well-behaving. So assume we can hit all these numbers. If we can hit all these numbers, then definitely bi times uji1, bi times, what should that be? Bi times uj1 up to bi times uj sigma will be linear independent because they are living in different places because these numbers are different. And because of the one-way well-behaving property, actually these will also be linear independent. This is actually what the one-way well-behaving property was about. So this is linear independent set, and if we then do the components-wise product with our code word, then we will get a space of dimension sigma, because this is the basis. And then this was the one argument. The other argument is if you take a code word and take the inner product with a components-wise product with everything, well, then we get a space that had dimension equal to the Hamming weight. Okay, so we have two spaces, and this space contains that space. That means that the Hamming weight of code word is at least equal to the sigma value. Okay. Now I'm going to talk about the dual codes. In the dual codes, we do not talk about what can be hit, we talk about what can hit me. So I'm not going to go through all these details, but I mean, it's the same thing as before, but instead of counting what I can hit, I count what can hit me. And the result is, if we have an index such that our code word inner product with BL is non-zero, but the inner product will all smaller indices equals 0, then the Hamming weight is greater or equal to this mu value. And the proof is, there are more proofs, but you can give a proof that reminds very much about the proof I just gave. So the game we play, if we have primary codes, we look at all the BIs that were used in the code construction, and the minimum distance is at least the smallest sigma value that we encounter. If we look at the dual code, well, then we have a lot of parity checks. But what we do is we look at all the non-parity checks and look for the smallest mu value, and that will be an estimate of the minimum distance. Okay. So the connection between primary codes and dual codes I try to explain here. So we have a basis G. So imagine that we have a generator matrix distribution. Then we have this basis G1 up to Gn, and we choose some of them for making our generator matrix. And we have this supporting algebra, the basis over here, which helps us estimating the minimum distance of the codes. If now we choose this H basis in this way, so it's basically, this is basically the inverse of this matrix over here, of course. But look, we changed the ordering of the basis of H, goes from n to 1 instead of 1 to n. If we do this, then we will have a very, very simple translation between what is going on the primary code level and the dual code level. So, of course, we will have some equality between codes. We have given one code described in primary description. We know how it looks in dual description. But the nice thing is that all this game with one-way well-behaving pairs translate directly. So all information we have about sigma and this row thing with respect to this ordered set translate immediately to row value with respect to H and mu value with respect to this set. And what is the implication? Well, the implication is if we need one more result. And the thing is that if you have a dual description, you can use Feng-Rao, the majority decoding algorithm, and Miura and Matsumoto, they showed how to do that actually at linear code level. So one thing is having supporting algebra. You can use the supporting algebra and have decoding algebra in there. But actually you can go to the linear code level and use this concept of well-behaving. So what we do, if we have an algebraic defined primary code, that might be defined over some algebra of higher transcendence degree, so we don't know how to decode it. But what we do is simply we translate it to the linear code level, and in that level, at that level, we can go to the dual code, and then we can apply this decoding algorithm. Yeah. So this is nice, but so look here. This is one example. We're working over F5, so we should have 25 points, but I only picked 9 of them. And then I have polynomials in 2 variables, and this is very natural: 1 x y, and so on up to x squared y squared. So this is what, and then I can choose from those to make a generator matrix. But if I use this correspondence, my H polynomials look this ugly. And I mean, I could look here and get some easy estimates on what will be the number of well-behaving pairs, which of these will hit another one, and so on. I could play with polynomials. But if I had to play with this and this together, it's not easy at all. So the result here is that up here you can get easy information about what is going on. Then you go to the code level and use this. And you can translate results and use that in the decoding algorithm for the dual code. Yes. Yeah. So what I have been claiming is that information from function field theory, Reedmuller basis theory, different kinds of algebra, order theory, actually what is going on is that you translate information there into information about this row value, about I only introduced one way well-behaving, but we also have a term weakly well-behaving or just well-behaving. I actually introduced the most restrictive one. And what is happening is that multiplication in this algebras corresponds to components-wise product. And what is nice about this bound on the primary codes is that recent list decoding algorithm by Lee and collaborators actually, and this is a method on a very high level, very clever, and the number of errors that is guaranteed to be corrected if we don't use the list decoding version is actually this footprint bound number that we derived. So this is nice that there is this connection. Yes. Yeah. And I don't know if you're familiar with generalized Hemingways, but generalized Hemingways is, generalized Hemingways. So, maybe I should start by saying where they come up. They come up if we want to analyze a wire subchannel of type 2 or secret sharing schemes. It's recently this result that the generalized Hemingways actually explains what is going on with secret sharing schemes. Okay. So let me just say that if we want to estimate the generalized Hemingways rather than only the minimum distance, everything we did translate immediately, really immediately. There's nothing to it. It's very simple. So let's just how much? Sorry, how much time do I have? Should I minus how much?
Yeah, 10 minutes.
10 minutes. Okay, I'm not going to use it. Okay, so I think I can explain what is a generalized Hemingway. So let's go through this definition, thinking of a space of dimension 1. If we have a code word, well, we want to know what is the Hemingway of it. Well, we can consider the space generated by that code word by multiplying by non-zero, by scalars. So think of this definition as this subspace D of our code is one-dimensional, so that corresponds to a code word. And the support, what does it mean? Well, it just means where all the entries where it's non-zero. So the number of such entries, well, that's the Hemingway of the word, right? And then here we have a code, and we look at all the different code words we can have, and look at the support. and we take the minimum. That's the minimum distance. And then generalized Hamming weight is just about, instead of taking only subspaces of dimension 1, we take subspaces of any dimension up to k. And do the same trick again. So if we have a subspace of dimension d, then it does not have that all covariates are non-zero, but if some of them are. Okay. So, and the claim is that this translates, everything translates into generalized Hamming weights. And I think this is my final, I just have to check, sorry. Yeah, this is my final slide, except for the conclusion. I just wanted just a quick result. So we again at this intermediate level. And let's look at generalized Reedmuller codes in this concrete case. So let's say if we have the numbers here, that would correspond to the Reedmuller codes where we go up to weight 3, right? 1, 2, 3, right? So the minimum distance is 10. We have it here. But what about the second smallest number of second smallest weight? So what is the second smallest weight? Well, if we look at this number, it seems that it is 12. Yes, but now we should be careful. But we cannot just use the method for anything, because we were playing some game with what is this as the leading monomial, where can we end up? So the danger here is that the leading monomial could be this guy. And we say that in the worst case, we have 10 non-zeros. And if this is the leading monomial, in the worst case, we have 12. But what if this is the leading monomial, but we don't have that many zeros? I mean, it could happen. It's only the worst case. So you have to analyze this. And this is actually the only proof I know where you use Buchwacker's algorithm in a proof. You take Buchwacker's algorithm is a way of deriving a Accrual basis for an ideal. And in the proof of that actually the numbers are, the second smallest weight is actually the numbers that we have as the second smallest number. We actually use Buchwacker's algorithm as at a theoretical level. Okay, and so we can, for m variables and then going up to degrees q to the power m minus 1, we can prove that the second smallest number is actually what we get. And then if we have only two variables, I mean, if we go here, the minimum distance, if we have this code here, the minimum distance is 3, and the second smallest number is 3 plus 1, so that will have to be the second smallest weight. It will have to be. So it's easy. So altogether, for m is 2, we know everything. And the nice thing is there's a thesis from 74, which says that if we have information about two variables, we have information about everything. So this is nice. So, in conclusion, I hope I managed to give you an idea that it is three levels. And it sometimes can help you, in my understanding, to understand what is really going on. I claim that actually what is really going on is you can see that at the very lower level. And well, so the low level description often captures what is going on, but as you probably realized, it can be quite technical. So, yeah. So sorry for that.
Are there any questions or comments?
Yes. When you